Um, Today is my turn to speak at this ungodly hour. I'll start by quickly reminding the punchlines of the two previous lectures, and then we'll go on. So first, in the first lecture, we discussed two-dimensional RG flows. In two-dimensional RG flows, there is a quantity, which is C, the central charge of this two-dimensional field theory, which has monotonic properties. C has monotonic properties in two dimensions in RG flows, but C has a plethora of other interpretations which are somehow more intuitive. So in two dimensions, C can be shown to be equal to the free energy of the system. That more or less follows from Cardy's identity about two-dimensional theories. That's more or less the content of Cardy's identity in two-dimensional theories. Or it also, you can think about it as a result of modular invariance. So that renders C a more intuitive notion of the number of degrees of freedom. So it's the free energy density, of course. C can also be shown to be equal to the density of states at high energies. And in free field theories, it also agrees. So this is in free field theories. In free field theories, it also agrees with what you would call the naive number of degrees of freedom. So it agrees with naive expectations. So that's the state of the art in two dimensions. I'll mention something important about two dimensions and other dimensions in a moment. So then we discussed three-dimensional theories. In three-dimensional theories, we found a peculiar candidate, which is the partition function of the theory on the three sphere. I should mention that C is also another equality for C. You see that C has many guises. So another equality for C is the partition function of the theory on the two sphere. Yes? So you compactify this two-dimensional theory on the two sphere, and C can also be interpreted as this partition function on the two sphere. Now, in the next lecture, meaning yesterday, we found a peculiar candidate in three dimensions, which was the partition function on the three sphere. And all these nice equalities in two dimensions are actually rendered incorrect in three dimensions. In three dimensions, the partition function is not equal to the free energy, the partition function of the three sphere. And it's not equal to any naive notion of a number of degrees of freedom. And so on and so forth. So we've discussed that, and there was even a more striking peculiarity that even topological theories had a non-zero contribution to the partition function over the three sphere. So that was the state of the art in three dimensions. And today, I'll jump to four dimensions. And the question is, what is going to happen in four dimensions given these rather different looking results in three dimensions and two dimensions? So in four dimensions, it turns out that the answer is, again, a partition function over a four sphere. So you see the pattern, it's always the partition function over the n sphere. In n dimensions, the candidate is the partition function over the n sphere. That seems to be the right conjecture in any number of dimensions. So in four dimensions, I'll explain that the correct quantity is, again, the partition function over the four sphere. That in four dimensions is, again, not equal to the free energy of the system in flat space. However, it's equal to the free energy of the system in hyperbolic space. Okay, so that's another interpretation of this quantity. In 4 dimensions, there are also trace anomalies, as I will explain, and this partition function over the 4 sphere is also equal to a trace anomaly. Okay, so this is some trace anomaly that I will explain in quite a detail. So that's more or less what we will see is happening in 4 dimensions. And one thing that's lacking in this picture is, of course, some more global view or an overarching concept that will explain why are all these things correct. And one striking candidate to explain these different results in different numbers of dimensions is something that I will address in the end of the next talk. And that's a concept borrowed from information theory, which is called the entanglement entropy. So one advantage of all these results is that they're all basically the partition function over the n sphere. So in n dimensions, the candidate is the partition function over the n sphere. That is good and well, but that does not have any intuitive meaning, at least not for me. That's a rather mysterious and abstract object in quantum field theory, and it's not directly connected to the number of degrees of freedom in any sense, or entropy and so on. But it turns out that there is a concept in information theory which is called the entanglement entropy. It further turns out that this concept of entanglement entropy can be extended or embedded in quantum field theory. So I'll explain how to define entanglement entropy in continuum quantum field theory. It's defined non-perturbatively in any quantum field theory in any number of dimensions. And then there will be another equality that you could add to this sequence of facts, which is that the partition function over the n sphere in an n-dimensional theory, we will show is equal to this concept of entanglement entropy in quantum field theory. So that will be another thing that I will emphasize. Yes?
This f function, the flow of it, can be described as a gradient?
Nobody knows. All right, so the plan for today is that I'll discuss mostly 4-dimensional RG flows. There aren't many things you can say about 4-dimensional theories, especially not about theories like UCD, which are inherently non-perturbative. But today, I'll show you completely new, well, not completely, but some new ways of thinking about quantum field theory in 4 dimensions or any number of dimensions, which allow you to prove results which are non-perturbative in nature about every 4-dimensional RG flow. I'll introduce some concepts which may seem a bit strange at first, but you get used to them and you'll see that they're quite powerful. Basically, the concepts are that of those of Spurian analysis. You do very sophisticated Spurian analysis for 4-dimensional RG flows. It's not the simple Spurian analysis that you're used to. It's a bit more sophisticated. You'll see that there are many things that go into this Spurian analysis. But in the end, it's Spurian analysis. So the content of that...
What is the concept?
Spurian analysis. Spurian. Spur. It's like trace in German. So you keep track of something. And you'll see that these tools, which are somewhat new tools in 4-dimensional theories, apply with or without supersymmetry. And you can use them to prove interesting results. And they also extend beyond this particular set of applications. You can use them in many other ways. Okay, so now I'll jump to 4 dimensions. So before I start really discussing 4-dimensional flows and all the technicalities and all the details that I need, I'll start from some mathematical interlude. I'll just tell you what is the solution of one particular mathematical problem that will be important when I discuss 4-dimensional flows. But for now, for the next few minutes, it will be a pure problem in mathematics. And this problem in mathematics will, of course, be very important for what I'm going to say. So in order not to have a digression later, I'll start with the digression now. So the problem in mathematics, so this is a problem in math. In any number of dimensions. Okay, so the problem in mathematics in every number of dimensions that I'm going to give you is the following. So consider a system or an action. It's a classical physics problem. So we study actions that depend on 2 fields. One scalar field tau and one metric field g mu nu. And this is stripped of any physical interpretation. I'm just showing that to prove well, to discuss some mathematical properties of this object. So we have an action that depends on some scalar in space-time tau, which from now on I'll call the dilaton. So we have an action that depends on the dilaton and on the metric field. This action is supposed to satisfy a few properties. Property number one is that it's gotta be diff invariant. So we have to maintain diff invariance for this action. What it means is that tau is a scalar on this manifold of space-time, and G mu nu transforms like a metric. Okay, so G mu nu is your common metric, and you're allowed to only write terms in this action which are invariant. The other property of this action is it's gotta be local. So I'm only allowing you, for some reason, local terms in tau and G mu nu. So integrals of local quantities. And the last part, which is the non-trivial part, is a while invariance. That requirement I'll relax in a few minutes, and you'll see why. So I require while invariance. What does while invariance mean? Well, tau can be thought of as some Gaussian bosons for some conformal symmetry. So the natural transformation law for tau is tau going to tau plus sigma. And the metric transforms like that. So G mu nu goes to G mu nu e to the sigma. So that's a well-defined mathematical problem. And the problem is to write actions in an expansion and derivatives or any other expansion you like, which satisfy these three properties. And I'll show you that there are some really strong consequences of these three requirements. And one of these consequences will be then relaxed when I give up on while invariance. And this will have a very, very clear physical interpretation. So let's start in 2 dimensions. In 2 dimensions, it's really easy. We can start to write actions which satisfy all these three requirements. In fact, the last requirement of that of while invariance can be sort of taken care of really easily by defining an auxiliary object, g hat, which is given by G mu nu e to the minus 2 tau. You see that this g hat is a while invariant by definition. So g hat is completely while invariant by definition. So in order to satisfy these three requirements, it's enough to write actions for g hat when g hat is treated like an ordinary metric, which are diff invariant. So if you have a diff invariant action for g hat, then you've satisfied local diff invariant action for g hat, you've satisfied all the three requirements. Yes?
What's the meaning of considering this spontaneously broken while invariance?
That's completely void of meaning at the moment. It's a mathematical problem. You'll see the meaning when I get to the physics. In the physical context, that will have a very clear interpretation. But at the meantime, this is just a mathematical problem that I'm set to solve. All right, so let's start writing actions in 2 dimensions. So this is now in 2 dimensions, which have all these three properties. And it's easy enough. The first thing you can write has no derivatives. It's the famous cosmological constant. So we have d2x square root of g hat. So that's the first thing you can write. And that has, of course, no derivatives. It obviously satisfies all the three requirements. Okay? Now you start looking for candidates with 2 derivatives. And this is where the surprise comes, the first surprise. There are no candidates at 2 derivatives. The only thing you can write in terms of this g hat, which is diff invariant with 2 derivatives, is the Ricci scalar. So let me denote the Ricci scalar composed out of this metric g hat as r hat. And writing this guy is not a good idea, because you know that in 2 dimensions, the integral over the Ricci scalar is a topological invariant. It's called the Gauss-Bonnet term. So that actually does not give any effective action. That's a vanishing object, or it's a topological object, so it doesn't really depend on anything. It's not a genuine 2 derivative term in the effective action. So we don't have an action in 2 derivatives. And that's one quick consequence in 2 dimensions of these requirements. So this is actually not interesting, because it doesn't lead to an actual action. But at 4 derivatives, you can have many interesting things. At 4 derivatives, you can have r mu hat, and many other things. So the problem in 2 dimensions shows up at 2 derivatives. You don't yet see why it's a problem, but you'll see momentarily. So in 2 dimensions, the fact that this is not a real local action, and in fact you cannot write any local action in 2 dimensions which would have 2 derivatives and satisfy all these 3 requirements, is something that I need you to remember. Okay? Now in 3 dimensions, there isn't really anything interesting that's going on. You can write a 0 derivative term, a 2 derivative term, and 4 derivative term, and so on. So in 3 dimensions, there isn't really anything that's going on. These peculiar phenomena are associated to anomalies, in fact. You'll see that this is very closely related to anomalies. So in odd dimensions, there is nothing interesting about these effective actions. It's only in even dimensions. So let's do now the 4-dimensional case, which is slightly more cumbersome. So again, at 0 derivatives, you can write the cosmological constant term. Oh, yeah. So you can write the cosmological constant term, which is easy enough. At 2 derivatives in 4 dimensions, there is no problem. The Ricci scalar in 4 dimensions is perfectly good. It's not a total derivative. It leads to local terms, which are non-trivial. And the problem, as you would guess, shows up at 4 derivatives. The analysis of 4 derivative terms in 4 dimensions is slightly more complicated because there are many options. So let me take you through this analysis quickly. There are 3 possible terms. I'll start it. Okay, where is the eraser? So let me just classify all the possible 4 derivative terms in 4 dimensions. And you'll see that something very similar to what we've observed in 2 dimensions takes place. So now I'm continuing that equation from here. So we have K1. So we have 3 independent terms that you can write a priori. K1 multiplies R hat squared. K2 multiplies R mu hat squared. And K3 multiplies the Riemann tensor squared. Okay, so these are all the candidates you can write down at 4 derivatives. There isn't anything else you can write down, in fact. I mean, you can write box R hat, but that manifestly is a total derivative, so I'm not going to even include it. Okay, so what I'm going to prove now, and that will take a few 2 or 3 minutes, is that all of these terms are in fact topological or have a very special property that I'm going to use in 4 dimensions, which I'm going to use very strongly. So what I'll prove is that 2 of these coefficients are topological, and 1 of them has a very peculiar property that will be important when I get to the A theorem. Right, so how to prove that? So it's slightly easier to use a different basis of terms. You can switch to a new basis of terms in terms of, so instead of using this Ricci and Riemann tensors, you can switch to the Euler density and the Weil tensor squared. Okay, the Euler density and the Weil tensor squared in 4 dimensions are given in terms of some polynomials of these guys. And the specific coefficients are that the Euler tensor squared has the Riemann squared, then minus 4 Ricci squared plus Ricci scalar squared. And the Weil tensor squared is given by R mu rho sigma squared minus 2 R mu squared plus a third R squared. So now I'll tell you what is the next step. The next step is that you, instead of using this basis, you use a basis that includes E4, Weil tensor squared, and Ricci squared. You can switch to this basis because you see that the coefficients are not proportional to each other. So now we have a new basis, including E4, W squared, and R. So now that becomes, so I can, instead of studying this basis, I can study K1 prime R squared, K2 prime W squared, and K3 prime E4. And that multiplies the square root of G hat D4X. And these are all hatted tensors in terms of the metric G hat. So K3 prime is a topological term in 4 dimensions. There is a generalization of the Gauss-Bonnet theorem that you've studied in undergraduate. For 2 dimensions, there is a generalization of this theorem to 4 dimensions. And E4 hat is a topological quantity in 4 dimensions. So that, again, is on the same footing as this R hat in 2 dimensions. That doesn't affect any interesting thing, any interesting observable that we'll discuss. This guy is also not important because it's the Weil tensor squared. And eventually, I'm going to discuss some physics in flat space. I'm going to discuss physics with a non-trivial profile for tau. So tau of x in the physical applications that you'll see, I'm going to discuss situations where tau of x is a non-trivial function, but the metric is flat. So then, if this is the case, then the headed metric, which I've defined, is conformal to flat space. And then the wild tensor drops out. So that will not be important for what I'm going to discuss either. So one remains essentially with one term, the Ricci scalar squared. And I need to give you, and now I'll give you an expression for the Ricci scalar squared in terms of this tau of x for a metric which is flat. And this function has a particular property that will be very important when I get to the physical application of all of this discussion. So you can compute r hat squared, square root of g hat, d for x, when the headed metric is conformal to flat space with a conformal factor tau of x. And that's easy enough. One finds a box tau minus d tau squared, d for x. Okay, this is a small computation that you can do. In fact, there is some factor here, like 36, but that's not important. So this is the formula that you get by using the familiar conformal transformation properties of the Ricci scalar. And to illuminate this formula a little more, I'll write it in terms of a slightly different variable, and here it's up to a coefficient. So in the terms of a slightly different variable, that takes the form psi box psi squared, where d for x, where psi is given by 1 minus e to the minus tau. So for this variable, which I can define, you'll see what's its physical interpretation. That looks like a box of something squared. So eventually, in the physical applications that will be clear today, the interesting physical question will be about light like psi which solves the Klein-Gordon equation. And in that case, the conclusion would be that basically nothing here contributes. So all the terms of 4 derivatives are immaterial in 4 dimensions. So we've seen that in 2 dimensions it's really easy. It's obvious that there are no 2 derivatives terms. In 4 dimensions it's slightly more complicated. There are no relevant terms. However, in the end of the day, also in 4 dimensions, when you look at light-like configurations, you'll see what's the physical interpretation of all of that soon. Okay, so this was the mathematical interlude, and now I'll get back to physics, and you'll see where these things come in. So I'll start from discussing the general idea, which is called Spurian analysis. And I'm sure that most of you know what is Spurian analysis. So as I said, Spurion means trace. Spur is trace. Spurian analysis is a simple thing that you know from quantum mechanics. I'll give you one example that demonstrates how you would use Spurian analysis if you did quantum mechanics 10 years ago or something, before knowing quantum field theory. So suppose somebody gave you the following quantum mechanical model, where there is some set of variables x, like x1, x2, x3, and there is some potential for x, but this potential contains an electric field that breaks the rotational symmetry. Okay? So the kinetic term admits some, let's say, SO3 symmetry. Suppose there are just 3 x's. So we have sum over I from 1 to 3. And suppose, so this is SO3 invariant, but the electric field breaks the symmetry explicitly down to SO2. But you can choose the direction of E to be whatever you want. So the question about such models, and suppose this potential has a nice vacuum, and there is a gapped spectrum, and so on and so forth. So all the nice properties you want are satisfied. So the big question that so the physical point that I want to stress here is that even though you've picked a direction in space-time, which is the electric field, and you've lost formally the rotational symmetry, it's still extremely useful, this whole SO3 symmetry. Even though it's explicitly broken, it's still useful. And why is it useful? For instance, suppose you wanted to compute the energy spectrum of the system. Okay? So suppose you managed to solve this model and you've computed the energy spectrum of the system. My claim is that even though there is no SO3 symmetry, you can use it to say something about the energy spectrum. And the thing you can say about the energy spectrum is that it's going to be a function of E dot E, for instance, right? So that's quite intuitive. I guess all of you understand that. And the reason is that you can, so how do you do it formally? You promote the electric field to something that transforms under SO3. Then X transforms under SO3, and also the electric field, which is a parameter in the theory, is now artificially made to transform under SO3. Then the whole thing is SO3 invariant, and once you do the path integral over X and you read out the energy spectra, it follows that the function of E must be SO3 invariant. So that leads to an energy spectrum which has this form, this functional form. I'm going to use virtually the same idea in quantum field theory in a context which I don't think has been used before. And I should stress that such ideas are really prevalent in quantum field theory over the last few decades. Pion physics rests very importantly on such ideas. So the Ludweiler-Gezer classification of the chiral Lagrangian terms is using very importantly various transformation laws of auxiliary parameters in the Pion Lagrangian. So this kind of ideas appear in quantum field theory in Pion physics. Maybe more importantly, or more impressively, Seiberg has used such ideas to prove very strong theorems about supersymmetric theories, where he promoted various background fields to superfields, and he used the superfield transformation properties of these parameters that a priori could break supersymmetry. So these ideas are very common in quantum field theory. Now I'm going to use them in a slightly new context, and I'll explain what I'm going to do. So I'm going to use them for RG flows. Again, I'm drawing the picture that I've drawn many times before. We have a conformal field theory in the infrared, a conformal field theory in the ultraviolet, and there is a crossover scale M. What does it mean, this crossover scale? It means that the Lagrangian of the theory is given by the conformal field theory that describes the microscopic physics deformed by a mass parameter for some relevant operator. So if this operator has dimension delta, and now this is 2 dimensions, okay? I'll start from 2 dimensions. If this operator has dimension delta, then the mass parameter would have dimension 2 minus delta. Okay, so this would be the Lagrangian of the theory, and this is what I mean by this picture. So this triggers normally a non-trivial flow that takes you to a completely different fixed point that you cannot even solve in perturbation theory. Now, what I showed you in the first lecture is that this conformal field theory has an anomaly associated to it, CUV. This is the central anomaly of the conformal algebra in 2 dimensions, and this one has a different anomaly, C infrared. In fact, many people asked me over the last few days if there is 't Hooft anomaly matching, why are these anomalies not equal? Okay? 't Hooft anomaly matching tells you that anomalies should be matched in quantum field theory. Here, the answer is obvious, because this anomaly is of the conformal group of this conformal field theory, and this anomaly is of the conformal group of this theory, while in the middle, I've broken conformal symmetry explicitly. Okay? So the conformal symmetry is broken explicitly, it's shattered, and there is no 't Hooft anomaly matching. 't Hooft tells us to match anomalies when the symmetries are unbroken. 't Hooft doesn't care whether the symmetry is broken spontaneously or not. 't Hooft only cares that the symmetry is preserved, the current is conserved. And in this case, the conformal symmetry is obviously not conserved. There is a mass term. So you've broken it explicitly, and there is no reason why these anomalies should match. In fact, I proved an inequality, a strict inequality, and they obviously don't match. What I'm going to say now is that the correct way to think about these RG flows, well, one way to think about these RG flows is very much like in this quantum mechanical model. The only object in this system that breaks conformal symmetry is the mass. So instead of studying this in the old-fashioned way of having the mass as a fixed parameter and thinking about it as a crossover scale, I will think about the mass as a function of space-time. So I'll promote the mass to a function of space-time. That's the main physical idea. I'll make it more rigorous soon. But qualitatively, you think about the mass now as a function of space-time. Of course, when this mass has is a constant space-time independent object, then you're back to the original setup. But you're allowed to study this path integral or this quantum mechanical model with a mass that is an arbitrary given function of space-time. It's an auxiliary object. It doesn't affect the dynamics. I'm just studying the theory as a mass, this theory with a mass which is a function of space-time. Now, if you study this theory with a mass that is a function of space-time, conformal symmetry is restored. And that's the crucial idea. Now, this whole thing is completely invariant under conformal symmetry. Completely invariant under conformal symmetry, because the only thing that violates conformal symmetry is the mass. So now, if you study the action or the partition function of this theory or the energy spectrum of this theory, if you study any physical object that is well defined in this theory, its dependence on the mass, where the mass is a function of space-time, will have to be consistent with conformal symmetry. So you see that it looks like I've tricked you, because obviously our G-flows break conformal symmetry, but this Spory analysis idea is powerful. It allows you to restore conformal symmetry formally. So for instance, if you computed the partition function of this theory, it would be some functional of the mass, which is a function of space-time. This partition function will have to respect conformal symmetry. That's my main claim. Okay? That's a consequence of Spory analysis. So let me give you an example. What kind of things respect conformal invariance? Things which are dimensionless. So there could be something like dm over let's say m to the 4. So something like that, which is without a scale, roughly. I'm going to make it much more precise. I'm just trying to give you the idea. So the effective action as a functional of this mass will have to respect conformal invariance. It has no choice. Okay? Now there will be some additional details about this partition function. For instance, there are anomalies here. So you have to be slightly careful when you do Spory analysis in the presence of anomalies. But forget about the anomalies for a second. The basic idea is to restore conformal invariance. You'll see how anomalies come back, and you'll see what's their role, what's their effect on this partition function. So at this point, I would like to ask whether there are any questions about the basic idea. Yes?
Can you do the same if you break conformal invariance by going to the Higgs branch?
Yes, that would be called spontaneous, the Coulomb branch better. Oh, it doesn't matter, yes. That would be called the conformal, spontaneously broken conformal symmetry. In that case, there would be absolutely no discussion. That would be, in the turf of 't Hooft, and you would have to match the anomalies anyway. I'm discussing now what normal people call normal RG flows, like what people do in condensed matter. When you go to the critical temperature, you deform the temperature, and you flow elsewhere. So this is a physical RG flow. It's not a spontaneously broken system. Also, I'm discussing 2 dimensions, so spontaneous breaking is not a good idea. This is an explicit RG flow. It could be one minimal model that flows to another minimal model by some mass parameter, and so on and so forth. What I'm saying is that I can trick you, and I can make this whole thing conformal invariant in disguise. And then once I have a functional which is conformal invariant, I will use the constraints from conformal invariance to say something about this system. And my goal will be, in the next few minutes, is that I'll show you a very quick proof of the Molotchikov theorem that does not rely on these identities between energy momentum tensor correlation functions and so on, that follows simply by studying this functional of the mass. It's a new proof of the Molotchikov theorem that follows simply from this, idea simply. Any other questions? Yes?
So it works also if the mass is dynamic?
So the correct way to think about it is a mass is a background field, and I promote it to a function of space-time. So I tell you, compute for me the partition function when the mass is a function of space-time. That's the correct way to think about it. It's not a good idea to make this mass dynamical, especially not in 2 dimensions. You could do it in higher dimensions in principle, but in 2 dimensions, it's not a good thing to write a kinetic term for anything. It's not. It's infrared. It's not good in the infrared. In 4 dimensions, it's fine. It's completely fine. What I'm saying is that it's completely not necessary. You could do that. In fact, you could do that, but I'm not going to do that because I have a much cleaner way of saying what I need to say, which is just to think about it as a function of space-time, and then you get a partition function, which is a functional of this function of space-time. So I could do that, but it's not necessary. It will just confuse. It will just confuse the dynamics of this theory. Now the dynamics of this theory is completely clear, and it's clear what I'm doing. Any other inquiries? Okay, so now I'll do it slightly more rigorously. I'll tell you how to do that. So in principle, a conformal field theory can be deformed by many mass parameters. So there could be an index I, right? There could be many operators with many mass terms. And so how do you do it really rigorously and in the most economic way? What you do is that you promote all the mass parameters, all the mi, to functions of space-time. So you could have any of these mass parameters a separate function of space-time. You could do that, but then that would be slightly more complicated to analyze because you would have many, many different functions of space-time. What I'm going to do is slightly more economical. I'll promote every mass term to a function of space-time, but they will all depend just on one common factor, tau of x. Okay? So I'm promoting all the mass parameters to functions of space-time, and this is the key prescription. And that, of course, makes physical sense because I want to restore conformal invariance. So to restore conformal invariance, it's enough to give one common dilation factor to all the masses. I don't need to do it for every separate mass, right? So now the claim is that the partition function, which is a function of this tau, has to be conformal invariant. Okay? So we now have a z. We have a Lagrangian for tau, which has to be conformal invariant. What does it mean? So to do it slightly more rigorously, you can also couple the whole system to a background metric field, which is a small metric. And then conformal invariance is simply what I wrote, what I started from today. So conformal invariance acts by taking the metric, by changing the metric via the usual Weyl transformation. Tau goes to tau plus sigma. So this is how I restore conformal invariance. Or in other words, you do a conformal transformation. You accompany this conformal transformation by a shift of tau with this Weyl factor, and then conformal symmetry is restored by definition. Because the only thing that violates conformal symmetry, forgetting about the anomalies for a second, are the masses. So if you rescale the masses, you restore conformal symmetry. That means that this set of transformations should be consistent with this Lagrangian of tau, but I am not really introducing a curved metric now. I don't need that. So what I need is the consequence from our digression for flat space-time. So in general, if you introduced a curved metric, the whole system, the Lagrangian would be a function of tau and g mu nu. And this Lagrangian would have to be consistent with this transformation laws. But I already analyzed the consequence of this transformation, the consequences of this transformation laws. So now I'm setting the metric to be flat again, and I recall what we got. Okay? So there could be a constant here. This corresponds to the So in the Lagrangian for tau, there could be the trace of the cosmological constant term. That would give you e to the minus 2 tau. Well, and I'll tell you where this comes from. Now there is no two derivative term for tau. This is because there were no candidates at two derivatives in 2 dimensions. And then there are some 4 derivative terms. And so on and so forth. This is the key structure of this effective functional. I remind you that this comes from square root of g hat. Okay? This was our cosmological term in terms of the metric g mu nu and tau. And g hat is given by g times e to the minus 2 tau. So when you take the square root of the determinant, you get e to the minus 2 tau. So there is something that does not depend on any derivatives. It's this guy. There is no two derivative term, and that's the crucial thing. And there are some 4 derivative terms. Okay? So this would be the correct answer if there were absolutely no anomalies anywhere. Okay? I assume that the whole system is completely conformally invariant. The only thing that violates conformal invariance are the mass terms. And this would be the conclusions if there are absolutely no anomalies. Okay? Is that clear? Yes?
Question. If we say that now we have that parameter m which also transforms, yeah? Then we have conformal invariant theory. And doesn't that mean that we're in a conformal point again and there is no flow? No,
that's exactly what I want to emphasize is not true. You remember this quantum mechanics model? So I've promoted the electric field to be something that transforms under SO3, but that does not mean that the quantum mechanics model is SO3 invariant. This is what people sometimes call selection rules. These are selection rules. These are not properties of the dynamical theory. The conformal symmetry here is not a symmetry of the theory. It's a selection rule for the dependence of the partition function on the parameters of the theory.
So we don't integrate in path integral on tau, on dilaton parameter?
You do not integrate. You do not pass integrate over tau. Tau is a given background function of space-time. The dependence on this function is studied here. So this is the dependence of the path integral on this background function. Yes?
So this is the effective action for tau after you integrate out
everything. Everything else. How do I know it's local? Yes, that's a good question. The reason is quite simple. So you see that what I've done, I'll tell you the physical answer. You can prove it rigorously, but I just tell you the idea. Why does it have to be true? So I promoted the mass parameters to functions of space-time in this fashion. Now you know that by the time you go to a conformal field theory, all the mass parameters are erased. And the only place where the dilaton appears is in mass parameters. Okay? So when you flow to a CFT, so in general, when you flow, in the beginning you turn on some relevant operator. it grows, it grows, it grows, and then it becomes irrelevant because it back reacts on itself. And in the end, near the CFT, the flow is described by an irrelevant operator that decays away. Okay? Since the dilaton appears only in these mass terms, what happens is that the dilaton does not couple directly to the conformal field theory in the infrared. It only appears inside these mass terms, so its effect dies off when you go to long distances. The conformal field theory itself in the infrared, or in other words, this object that appears in the deep, deep infrared, is conformal invariant by itself, right? It does not need this dilaton to fix the conformal invariance. What this dilaton does is it fixes the conformal invariance of the whole system. But it does not need to be fixed in the infrared. And it does not need to be fixed at very short distances. It only needs to be fixed around the crossover scale. So the dilaton couples only to the physics at the crossover scale. And it dies off at very short distances and at very long distances. So this is why the effective action for tau must be local. It doesn't couple to massless degrees of freedom, so it cannot have branch cuts at zero momentum and so on. It can have branch cuts at non-zero momentum around the crossover scale, but it must be a local function because it does not couple to strictly massless degrees of freedom. Okay, that was a very good question. Any other questions? Okay, so now the absence of these two derivative terms, suppose you didn't know anything about anomalies, you just did this trick, and this would be your conclusion. This could be a way to discover anomalies, in fact. This is, if you didn't know anything about anomalies, you never heard of it before, you just repeated this old-fashioned logic of Spory analysis, this conclusion is alarming. And this would be a way to discover anomalies. Okay? And the reason for that is that two derivative terms are, in any generating functional, are extremely important. Two derivative terms in unitary field theories have to be positive. They're not only non-zero, they have to be positive by reflection positivity. Because this effective action for tau, this effective functional for tau, is merely a bookkeeping device for some correlation functions in this theory. Tau couples to the mass term, which, well, tau appears in this mass term, which means basically that tau couples to some operators in the physical theory, in the physical unperturbed theory. So this is a bookkeeping device for two-point functions. The two derivative term encompasses some two-point functions. And these two-point functions cannot vanish. And the fact that there are no two derivative terms is extremely alarming, basically. This violates unitarity. You'll see that the day is saved by the presence of anomalies. So what I will show next is that, in fact, two derivative terms are completely fixed by anomalies. And from that point, it's sort of clear because you see their absence if there are no anomalies. In fact, it turns out that this effective functional contains a universal term, which is completely fixed by an anomaly. And then I will be able to prove the homological theorem, basically because it has to be proportional to C. Okay? So what the answer will be, I'll just tell you what the answer is, and I'll prove it in a second, that this thing must be proportional to an anomaly. That's clear from this analysis. But the precise dependence on the anomaly is the following. You get C of V minus CIR d tau squared. This term cannot be generated by any local term in terms of tau and g mu nu hat, which is Weil invariant. And therefore, it's related to the anomaly. And this is the particular coefficient that appears if you do the calculation. It's CUV minus CIR, where CUV is the physical anomaly at short distances, CIR is the physical anomaly at long distances. And this is what shows up in the effective functional for tau from Spurian analysis. I'll prove that in a second. But just to jump to the final conclusion, because of positivity requirements in quantum field theory, the coefficient of this kinetic term, in quotation marks, of course, this is no kinetic term for any propagating particle. This is just a generating functional. But this is a bookkeeping device for a two-point function. And since two-point functions have to be positive, because they look like the square of something, that will have to be bigger than 0. And that will establish the Zamolodchikov theorem. Now I'll go through the details a bit more. Is that logic morally clear?
So this e to the minus 2 tau has no consequence for you?
This has consequences. So this is the bookkeeping. So I'll tell you, I'll just explain intuitively what's going to happen. Tau is a bookkeeping device for correlation functions. This is a bookkeeping device for some correlation functions at 0 momentum. This is a bookkeeping device for correlation functions to the derivative of some correlation functions at 0 momentum, and so on. So when you increase the number of derivatives, it's a bookkeeping device for correlation functions with more and more derivatives in some sense. And you can prove that any of them has to be positive. So once one of them is absent, your unitarity is basically out of the window. You have to have all of them. At 4 derivatives, you can check that there are no problems. You get the right terms. At 0 derivatives, there is no problem. You get the right thing. However, this is absent if there are no anomalies, which is why it has to be proportional to the anomaly. And a small physical argument shows that this must be the difference between the anomalies. And then you're done, basically. I'll show more details, of course. It's not.
So if e to the minus 2 tau was absent, it will have been also a problem?
In fact, no. And the reason is that this is a bookkeeping device for some zero momentum correlation functions. And these 2-point functions are basically diverging. They're not universal. So if it were absent, you would say that, okay, somehow you chose a bad scheme where you set the cosmological constant to 0. You see that this is the cosmological constant. If tau is a constant, maybe this is a good physical argument to make. If tau is a constant in the problem, right, then you're studying the partition function of the original field theory, unperturbed, with no space-time dependent object. And then the partition function is the cosmological constant by definition. So this thing, the coefficient here, is what Einstein would call lambda, the cosmological constant. And that's an ambiguous quantity. That's not a good object to talk about.
And
so
it could have both sides. And it could certainly have both sides.
That's right. It could have any sign, and it's not a good object to study. It's completely ambiguous. There is no field theoretic way to study it. However, this object is absent if there are no anomalies. The fact that it's proportional to an anomaly suggests you already that it's going to be finite, meaning that this object has enough derivatives to render it finite in any consistent quantum field theory. And that's a good object to discuss. That has no counter terms. It cannot be subtracted. It's an anomaly. And it's completely universal and finite. So this is a proof of Zamolodchikov's theorem, which you see in nature is completely different from the original argument. Also, I want to mention that the 4-dimensional argument will be completely isomorphic. Instead of discussing 2 derivative terms, I'll just discuss 4 derivative terms. But it's going to be exactly the same story. Yes?
It's sort of interesting, in the odd dimensions, where you were proving, arguing that z, the log z was decreasing, you went through non-unitary theories.
Yes. Yeah, this argument with putting supersymmetry on the sphere had to invoke non-unitary theories.
So it was as if you turned on some deformation. I mean, that would have corresponded here, turned on some deformation that wasn't unitary. We're in between.
That's right.
Unitarity is crucial.
Yes, yes.
Do you understand that difference in approach?
This kind of arguments obviously carry over. They're applicable only in even number of dimensions. If you did this analysis for the generating functional for the dilaton in odd dimensions, there would be no consequences. But I can explain why, physically. This is, in nature, a local object. I'm studying local integrals of local functions, and they are bookkeeping device for correlation functions, which are local. In 3 dimensions, we don't have a local picture of this F theorem, of this F conjecture, this conjecture about F. The only way we can present this conjecture is via an integral over a sphere. We cannot really stick our teeth into the problem in terms of some local object. If I knew how to represent this partition function over the sphere as a local object, I would know what to do. But I don't know what to do. And here, while in even dimensions, the conjecture is about the partition function again, but then it's miraculously also equivalent to some anomaly. And anomalies I know how to write in terms of correlation functions. And then I can use Weizmann conditions, anomalies, Spory analysis, whatever I want. And so this approach is basically absent in odd dimensions.
In dimension, you are not going to put d tau cubed kind of thing.
Yes, because of Lorentz invariance. You would think that d tau cubed would, yes. Yes. Of course.
That's something that's still missing because you expect there would be a local description of 3 dimensions.
Yes, I completely agree. In fact, we've had many discussions with Nima over the last few days over how to render this partition function over this sphere, a local quantity, how to understand it in terms of local physics, and we don't know. I don't think anybody knows how to do that yet. But in even dimensions, we have this dual formalism, where we have a partition function over the sphere, but that also is a local quantity, some anomaly. So we're lucky in that sense. Okay, so now I'll tell you physically. Yes, Nima?
Just if we could ask a question and expand a little on the question of why the action is local.
Yes.
Because here you are promoting the mass parameters that are breaking the formal symmetries, the relevant operators that you added to a background field. And now you're about to treat the anomaly as something that we forgot
Yes.
Something else that we could do is imagine talking about the full regulator theory, including all the regulators, everything which is up there, and promote everything, including the regulators, right, to background objects like that. If we do that, then there's no anomalies in this language. Then we just have to write every diff and file invariant statement that we can. And the fact that so what happens to the argument then? So we could do that. And I suppose what happens is that in that language, it's just the usual thing with anomalies. Now there are terms that are not local.
Yes, it's crucial. It's crucial that to understand that in quantum field theory, when some identity like that is violated, it could be violated in two ways. One way in which it could be violated is by an explicit violation. An explicit violation is an operatorial violation that that exists in correlation functions at separated points. The mass terms are, of course, an explicit violation of this symmetry. The anomaly is not a violation of this identity. It only appears as a violation of this identity in auxiliary, if you add additional auxiliary fields like background metric and so on. So you can separate the two. You can decide that you promote these mass terms to be functions of space-time while keeping the anomaly as it is.
Precisely because it is an anomaly.
Yes, because it's an anomaly, you can identify the short distances where you define the theory. And the short distances you just replace, basically this is the Lagrangian, and all you do is you do that. And that's perfectly well defined.
All I want to say is that if you took the full regulator theory, including all the regulators at the top, promoted all the mass parameters to just did exactly what you did, not just for M, but for the complex
Yes.
as well, then we would rediscover the anomaly.
That's right.
In terms of some non-local objects.
Yes.
Which are generated.
That's correct.
Just
That's correct. That's correct. Yes, that's correct. I'll now explain how to take anomalies into account and how to explain that the coefficient is the difference between the anomalies. I'll do it quickly. So I analyzed previously terms which are while invariant, local, and the diff invariant. If there are anomalies, this famous functional of ours, tau of g mu nu, if there are anomalies, then this functional does not have to be while invariant anymore because the anomaly is in while invariance. And so instead of the condition that we've solved previously, the condition that we solved previously is that this is while invariant under the while transformation that I defined. If there are anomalies, then this is not the right equation to solve. The right equation to solve has the anomaly on the right-hand side. And in 2 dimensions, the anomaly is C times sigma times the Ricci scalar. So now this is not a topological term because sigma is any function. Sigma is any function of x. Okay? This is the anomaly in 2 dimensions due to conformal invariance. So the equation that we've solved is not the right one. This is the right equation to solve. However, you see that if you find a particular solution to this anomaly equation, then you can add any of the solutions that we found before. That's an inhomogeneous equation. So once you find a representative for the anomaly, you can add any while invariant term to the action. That won't change the fact that it's still a solution. So solving such equations where you look for an action whose while variation is this thing, and this action is local, is known as the Weizmann problem. And Weizmann solved it in the context of quantum physics many, many years ago. Here, the solution is quite simple. I'll just give you the answer, and you can check as a small homework exercise that this answer that I'm giving you satisfies this equation. It's a solution to this inhomogeneous equation, and then you can add any of the things which are homogeneous that I've already written for you before. So it turns out that the solution is tau r, except for one thing that I'll explain in a second. Tau r is a very good object to start from, because if you remember, the variation of tau is tau goes to tau plus sigma. So when you do the variation of tau for this section, the sigma variation of tau, you pick up exactly the thing you expect. So there is a square root of g. You pick up exactly the right term that you expect. But that is not the full story. There is something which is called the Weizmann term in this problem. That's because the Ricci scalar is not while invariant. So when you do a while transformation for the Ricci scalar, you screw up the fact that you need to get exactly this equation, and you need to fix this by something. And the thing you fix it by is called the Weizmann term, and I'll explain the physics of this in a second, and I'll also remind you how this comes about in pion physics quickly. So this is the full answer, up to any while invariant term, because it's an inhomogeneous equation. So you see that the anomaly, the conformal anomaly, as I also mentioned it a second ago, is not a violation of the symmetry in flat space. It only manifests itself in curved space. But when you want to write an effective action which reproduces the anomaly, it is forced on you by this requirement to add a term which is non-vanishing even in flat space. So the naive thing you would add, tau times r, vanishes in flat space. But even though the anomaly exists only in curved space, when you write an effective action that reproduces the anomaly, it is sometimes forced on you to write a term which does not vanish even in flat space. Okay? These terms are known as Weizmann terms because you see that they're quite subtle and somewhat unintuitive. It took some time before people realized that they exist. But this is completely necessary for the consistency of the variation of this action. In pion physics, when you try to do the same exercise for the chiral anomaly, the first thing you write is pion times FF dual. Yes, this is what reproduces the non-abelian chiral anomaly at first order. But it turns out that you need to sort of fix that for various reasons. And you end up introducing a term which is quintic in pions and has 4 derivatives. And its coefficient is completely fixed by an anomaly. That is what people traditionally call the Weizmann term. But you see that also the conformal symmetry has a Weizmann term. The conformal symmetry is a non-abelian symmetry, and therefore it has a Weizmann term. Abelian symmetries don't have Weizmann terms because you don't need to fix the transformation laws. So in quantum electrodynamics, you don't need, if you add the massless fermion, you won't need well, if there were some symmetry breaking and so on, you won't need a Weizmann term. But in non-abelian symmetries, you sometimes need Weizmann terms. So instead of the problem that we've solved, we need to solve that problem, but the solution is easy. You take this inhomogeneous solution and add anything that I've talked about before. And you notice that to our surprise, or, well, that had to be the case because of unitarity, it's a 2-derivative term, exactly of the kind that I was missing when I set the metric to be flat in the previous analysis. And its coefficient is C. So now I repeat the logic of Spurian analysis, and I'll explain why when you do the path integral over this whole system, you have to add this term where C is replaced by the difference between the two C's with this dependence on tau. The argument is very simple. You have so the theory is that, so let's start. The theory defined in the ultraviolet is the conformal field theory in the ultraviolet plus these mass terms, which with some power 2 minus delta, multiplying operators with dimension delta. This system is conformally invariant if you accompany the transformation laws of the fields by the transformation of appropriate transformation of the mass term. But there is an anomaly. So in fact, the variation of this thing under conformal transformation is proportional to C uv, because this is the only place where you get an anomaly from, times sigma r, square root of g, d2x. Okay? So the defining theory is not conformally invariant because of the anomaly, and the coefficient is exactly CUV. This is a property of the defining theory, and by definition of the Wilsonian procedure, this has to be property of the theory at any other scale, because if this is the defining property of the theory defined at short distances, the very same transformation property has to be true at any other scale, whether or not you integrated out your fields. That's the definition of the Wilsonian procedure, that you don't change the fundamental properties of the theory, you just integrate out stuff. But we know that when you've integrated out enough of these mass terms, you've integrated out all the fields, you have flown to the conformal field theory in the infrared. And that, by itself, only contributes CIR to the anomaly, not CUV. Therefore, the partition function for this mass term, which is a function of space-time, has to soak up the difference between the two, such that the full transformation of the partition function at low energies is equal to the transformation property of the partition function at the defining scale. This is why the coefficient in the effective action for the dilaton has to have the coefficient is CUV minus CIR. It soaks up the difference. A very similar thing happens in 't Hooft anomaly matching when you have spontaneous symmetry breaking. If you flow from a theory with one anomaly to another anomaly, and there is also a spontaneous symmetry breaking in between, the pion effective action would soak up the difference between the anomalies of the infrared and the difference between the anomalies in the UV and the infrared. That is what would happen if you had a 't Hooft-like scenario with chiral symmetry breaking. Here I'm discussing conformal symmetry breaking, but it's the same idea. The dilaton must soak up the difference between the anomalies. Okay, so now I'll show you. So this implies immediately Zamolochikov's theorem, because we found that the effective action has the following form. CUV minus CIR, and then there is this cosmological constant term with some arbitrary, well, it's divergent, so it has an arbitrary coefficient. And then there are other things. So we found that this is the form of the effective action for tau, based on Spurian analysis and taking into account the subtle effects of the anomalies. That proves that CUV minus CIR is positive, which establishes Zamolochikov's theorem. In fact, you can do much more here, and if you want to see that this is really the old good Zamolochikov theorem, you can do a bit more. That will be, well, that may be slightly over the head of some of you, but I'll make this argument for people who know slightly more. So tau is something that appears in mass terms. Therefore, tau couples to the energy momentum tensor. If you look at the linear couplings of tau to the physical old good theory, they basically couple to the trace of the energy momentum tensor, which is a non-zero operator in the theory. So to compute this two-point function from first principles, basically what it encodes T mu mu, T mu mu. This is what this is a bookkeeping device for. Because it has two derivatives, by dimensional analysis, in the end, this coefficient should be equal to this kind of integral, just by dimensional analysis. So the sum rule that we get from this story is that CUV minus CIR is equal to this thing. This is an advanced comment just for people who are interested. So the fact that the coefficient at low energies of the background effective action for tau is CUV minus CIR allows you to write a true sum rule, which is completely convergent because of this y squared. So that makes it convergent at short distances. There are enough factors of y to make it convergent in any field theory at short distances. And also at long distances, it's easy to prove that it has the right dimensions to be convergent in any field theory. And this sum rule, well, you fix the coefficients in this thing, and the coefficient here is exactly the same that what comes out from Zamolochikov's argument. You remember that this sum rule was one of the first things I wrote in the first lecture? Well, that was the conclusion of the first lecture, this sum rule. And once you fix the coefficients, they completely coincide. Once you fix the coefficients in this procedure, you do this, everything completely coincides, and that's the old good Zamolochikov sum rule, which is another, of course, which is positive manifestly from this approach or this approach. Okay? So this is basically the story in 2 dimensions. You see that it's a slightly non-trivial version of Spurian analysis. It's a slightly non-trivial version of Spurian analysis because there are anomalies lurking, but then these anomalies are under complete control. And then this proof of Zamolochikov's theorem is rather different than the original one, but you get the same sum rule as a consequence. Any questions before I switch? Yes?
You start with a background field that is tau.
Yes.
And then you see that in the IR it becomes dynamical.
I didn't say it. No, it doesn't. I never pass integrate over tau.
Ah, okay.
This function for tau is a bookkeeping device for correlation functions in the original massive theory. Okay? So it's a bookkeeping device. It's true that it has something that looks like a kinetic term, and string theorists would call this non-critical string theory, and so on. They would pass integrate over tau. But for me, it's just a bookkeeping device. And I know the coefficient of this bookkeeping device because of the Spurian analysis. Yes?
Can you extrapolate between the IR and UV using these arguments, or just get the difference?
So, you know, there are 4 derivative terms, 6 derivative terms in this bookkeeping device, but these are not universal. What does it mean that they are not universal? They do not only depend on the anomalies. They depend on the particular relevant operator that you've added with particular coefficients and so on. They depend on the actual dynamics. The 2 derivative term is very special because this is the only term in the system that vanishes without anomalies. So if there were no anomalies, that would be 0. Therefore, it's sensitive only to the anomalies, basically. So that's a universal term, which allows me to derive a theorem. You can try to do much more than what I did here with this kind of ideas and tools. And in fact, you can do many other things. I'm just presenting you one application of these ideas. But there are many others that you can think about. Yes?
So one of your points was that you can
from unitarity.
You start with the theory, and you add a term which breaks Lorentz invariance, not conformal invariance.
Lorentz, yes.
Yes, and then you can also elevate the coefficient into a field.
Yes, you can. If you had the Lorentz breaking field theory, you can of course promote the coefficients to be some functions of space-time and then restore Lorentz invariance.
So would you then discover anomalies in 2 or, I don't know, 8k plus 2 dimensions?
Gravitational anomalies, 4k plus 2 anomalies. That's an extremely good question that I know many people are working on in this language. Yeah, gravitational anomalies don't exist in 4 dimensions, but in 2 dimensions and in 6 dimensions they exist. And you can try to see what I've completely ignored here, gravitational anomalies, as you've mentioned, because I imposed diff invariance on the effective functional. But it's an interesting question to generalize what I said here in the presence of gravitational anomalies. I was completely sidestepping this issue, but some people are working on that, on including that. In 6 dimensions, that would be important. Yes. Any other questions? Okay, so this is basically the story in 2 dimensions. In 4 dimensions, it's not dissimilar. The logic is almost isomorphic. I'll go through the argument in 4 dimensions. And given all these facts, it shouldn't surprise you that it's so similar. So now I'll quickly go through the argument in 4 dimensions. I'll try to finish it in this session. And in the next section, we'll discuss a bit information theory and entanglement entropy, and how this may connect to this, and how these ideas may connect to our G-flows. One thing which is funny about this proof of Zamolodchikov's theorem is that it does not hinge on finding a curious function that satisfies a curious differential equation, which looks a bit miraculous. Here it's very physical, and indeed it's generalizable to any even dimension, this kind of logic. So that's one thing to keep in mind. So now, again, same picture, only 4 dimensions. And what I'm going to say now applies even to QCD. So there aren't many arguments in quantum field theory which apply non-perturbatively to QCD, and that's one of them. I'm going to think about QCD in the Spurian analysis language, where you promote lambda QCD to a function of space-time, essentially. And you study the partition function as a function of lambda QCD. Okay, so now the Lagrangian differs from the previous one just by the fact that there is a 4 instead of 2. So we have M4 minus delta, O delta, and we have a conformal field theory in the UV. That could be any conformal field theory in 4 dimensions, and that could be any other conformal field theory in 4 dimensions to which you can flow. I'm now repeating the argument. We start again without anomalies. No anomalies. And we write an effective generating functional for tau. It's again local, but by the same reasons as before. One can refer to the same kind of arguments that decouples in the deep and the infrared and deep UV to justify writing a local action for tau. And now the Lagrangian for tau is the following. So again, we have the cosmological constant term, lambda to the 4. This multiplies in 4 dimensions e to the minus 4 tau instead of e to the 2 tau in 2 dimensions. That's merely dimensional analysis. That's again an ambiguous term. It's there in the background generating functional for tau. It's not very illuminating. Then we have a 2 derivative term. There is no problem with 2 derivative terms in 4 dimensions. We have the Einstein-Hilbert guy, and one finds tau. One finds e to the minus 2 tau, tau box tau. This, in fact, is also divergent in 4 dimensions. That's still not a good object to discuss. The coefficient of this is still UV sensitive. It has a quadratic divergence. Okay? So that's still, it's there, so it doesn't violate unitarity. We don't have a violation of unitarity at 2 derivatives, but it's still divergent. So it's not a good object to discuss. Then we get to 4 derivatives, and these guys are finite. They don't even have a log divergence, which you can prove. What we found is that if there are no anomalies, the dependence on tau at 4 derivatives was very severely constrained. We had only this Ricci scalar squared, and that was the only thing we could write down. So we had box tau minus d tau squared. And then we have 6 derivatives and so on. So at 4 derivatives, we could write only one object. So there is a slight difference from 2 dimensions. In 2 dimensions, we didn't even have a candidate at 2 derivatives. In 4 dimensions, in fact, there is a candidate at 4 derivatives. So there is no immediate contradiction to unitarity, but you'll see that it's slightly hidden. There's still a contradiction to unitarity, it's just more hidden. To see that this is not enough to reproduce unitary correlation functions in the ultimate theory, where this is just a bookkeeping device for this ultimate theory, one switches to this variable psi, which is 1 minus e to the minus tau. That's just a quick way to see that this still violates unitarity. And this would be a way to discover, again, anomalies in 4 dimensions. So in terms of this variable psi, the cosmological constant term is 1 minus psi to the 4, right? So this is the cosmological term in terms of this variable psi. The Einstein-Hilbert term looks like psi box psi with some 1 over 1 minus psi squared. That's how the Einstein-Hilbert term looks like in terms of these variables. And this guy looks particularly simple in terms of this variable psi. It looks like a box psi squared, which is what I wrote before, and there's 1 minus psi to the 4. And then there are 6 derivative terms, 8 derivative terms, and so on. So I switched to this variable psi, and this is how it looks like. So there is a nice 2 derivative term, no problem with unitarity here. There is a 0 derivative term, which is the famous cosmological constant. And there is a 4 derivative term. So apparently it's all fine. However, this violates unitarity. This is not enough to reproduce unitary correlation functions, unitary 4-point functions in 4 dimensions, because this is a box psi squared object kinematically. So it gives rise to unitary 2-point functions with 4 derivatives, but it does not give rise to unitary 4-point functions with 4 derivatives. In other words, if you scattered 4 psi's, so psi is not a propagating field. So what I mean when I say scatter psi's, what I mean is that you couple psi to the operator, to the appropriate operator in the underlying quantum field theory, and then this is basically some blob. So we have this kind of blob where psi is an external leg. Sorry, I'll draw, this might be too small. I'll draw it slightly bigger. What is what?
I mean, it works nicely, but what is psi? Why do you like it?
I mean, in psi, it just makes clear that there is a certain correlation function which is not unitary, unless there are anomalies. So it's a way, I mean, it's a quick way to get to the chase.
I understand, but I say still you have a particular form. What does it mean anything, or is it not?
So you're asking if I have some deep interpretation of this psi?
Yes. Shallow or something.
I think, well, this is something that Nima explained to me a few months ago. I think that in terms of this psi, the conformal symmetry acts somewhat like the Galilean group. And you can see that by Galilean symmetry, you can only write box psi squared and not the term that is missing by unitarity. Is that correct? Yeah. So basically, this guy looks, if you expand it, I think it looks like the transformation law for psi looks like the conformal Galilean symmetry. And then the only thing allowed by conformal Galilean symmetry is this guy, but not the guy that is missing by unitarity, which I'll explain in a second. All right, so this is not a good, sorry, this is the way to draw it. So psi is a background field, and like in old-fashioned notation, I'm sticking circles for psi where I have insertions of this background field. It's not a dynamical object, it's just a background field. So I have 4 insertions of this psi now, okay? So this diagram is non-zero because there is some 4 psi interaction coming from here at 4 derivatives. I'm expanding in derivatives, so I ignore the 2 derivative terms and the 0 derivative terms. Let's just focus on 4 derivatives. 4 derivatives, there is something that comes from here. It looks like box psi squared times psi squared. However, I take all of these insertions, all these background insertions to be null. So they have all momenta. All of them have some momentum, K1, K2, K3, K4. And I'm choosing each one of these Ks to be null. Of course, they are also conserved. The sum of the Ks vanishes. So Ki squared is 0, and the sum over the Ki is also 0. That's momentum conservation. And that's a non-trivial condition, which I'm choosing. So each of this momentum is null, and the sum is 0. You see that the existing term in my Lagrangian, box psi squared, would predict that if I choose all these insertions to be null, then this 4-point function is 0. Okay? Because I don't have any candidate here that would be non-zero when all the psi's are null. All right? If I had something like deep psi to the 4 at 4 derivatives, then when all the insertions are null, there would be a non-zero answer, because you could dot the case in various ways and it would be non-zero. But with this Lagrangian and 4 psi insertions, there is no candidate to yield a non-zero correlation function of this kind. This violates unitarity. You can prove that when you have 4 null waves of some operators coming in, it must be non-zero. In fact, it must be positive. That follows from the optical theorem. The way to prove that, so let me explain how the optical theorem shows you that this must be non-zero, this particular correlation function, when all of them are null. So assume that this momentum is null, this momentum is null, this momentum is null, and this momentum is null. And further, assume that K2 is equal to K1 minus K1, and K3 is equal to minus K4. So the outcoming null waves are identical to the incoming null waves. Now what you do is you cut this diagram in the middle. That picks up some states in QCD, or whatever theory you're discussing, some non-perturbative states in QCD. This is some 4-point function in QCD, which is saturated by all the states in QCD, or any theory that you like. And because the incoming states are identical to the outcoming states, and importantly, because each one of them is null, this is the only possible unitarity cut. There can be no states propagating in this cut, because this momentum is null. There can be no states propagating in this cut, because this momentum is null. This is very important. So because it's a 4-point function, because each one of the insertions is null, cutting it here in the middle shows that this must be the square of something by the optical theorem. So when you cut something in the middle, unitarity implies that this must be the square of the amplitude of sending 2 null waves and getting something. And this something must be non-zero, so you get a non-zero answer in any unitary theory. This is why there is a problem in unitarity, with unitarity in this Lagrangian, unless deep psi to the 4 is present. But deep psi to the 4 is absent if there are no anomalies. So what one has to do is to repeat the previous argument, including anomalies, solving the Weizmann condition in 4 dimensions, which is slightly cumbersome. It's a somewhat technical exercise. It can be done. And it turns out that there is, again, a Weizmann term in 4 dimensions. So like we had the Weizmann term for the conformal group in 2 dimensions, there is a Weizmann term for the conformal group in 4 dimensions. And in fact, it turns out, even more surprisingly, that there is a Weizmann term in 4 dimensions for one of the 2 anomalies. In 4 dimensions, there are 2 choice anomalies, which are called A and C. I'm not going to discuss too much about them. But it turns out that one of these anomalies, C, is completely trivial. It's like the axial anomaly in QED. It's a billion. The A anomaly, which is exactly the guy which is corresponding to the partition function over the 4 sphere, has an anomaly, has a Weizmann term, and it leads precisely to this deep psi to the 4. And again, by the same token as before, you can argue that the coefficient must be the difference. And then it's positive, and that's it. And this proves the A theorem. Yes?
Can there be that the higher order terms in derivative change your argument? Or
No, the argument is about the 4 derivative Lagrangian. So unitarity, this argument with the cut, applies order by order in derivatives.
But this argument will not apply to the higher dimension. Then you can cut in more ways.
Excellent. So now you're asking me what would happen in 6 dimensions. Okay, I'll just this is a comment for the experts. So first of all, 4 dimensions is interesting because we have 4 dimensions, and this applies to QCD. So it's this argument. So it's interesting already in 4 dimensions, even if it's not. I don't know how to do it in 6 dimensions. But you're right. In principle, in 6 dimensions, well, one can do the analysis. I'll just tell you what's the answer. One finds that unitarity is violated in a 6-point function. But with a 6-point function, it's very hard to imagine any kinematics for which you can use the optical theorem rigorously, because there are many cuts, and they come with different signs. So I don't know how to prove the analog of the A theorem in 6 dimensions. The argument itself goes through. There is a term that is missing, but I don't know how to prove that it's positive, because there are too many kinematical options in 6 dimensions.
There's another little point which I'm sure is proved. In the case two operators. Violation of utility, I mean, what you really show is that the operator, positivity assures the operator is either 0 or positive.
Oh, you're saying that it's bigger or equal?
Yeah, just a 2-point function here. The 4-point function, what you're really proving is that the product of two operators both on the light cone is 0. Is that, from that, can you conclude that the operator
So, wait, so the question is about 4 dimensions? In 4 dimensions, it's really a 4-point function of the energy momentum tensors in a light-like configuration.
So therefore, using crossing, etc., you conclude that the product of two sides.
To going to anything.
Two light-like products. Well, actually, even by crossing any matrix element.
Yes.
So the operator is 0, but it's not an arbitrary operator. It's restricted to the light code.
Yes.
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 Does it follow rigorously that the operator of psi is 0?
You're asking, I think that, let me just understand. You're asking whether, yes.
If you have,
yes, I understand.
You prove immediately by using crossing analyticity that any matrix element of the operator is 0, therefore the operator.
That's right.
But here you're proving the product of two operators, both of which are restricted to the light cone.
Light cone, yes.
Any matrix element. But that's a more complicated statement about the product of two operators restricted to the light cone. Is there an analysis that then proves using, you presumably have to use some kind of analyticity again, that means that the operator itself is 0 as an operator?
That's right. I don't think that is necessary for what I'm saying. What I'm saying is that.
But unitary only gives a greater or equal to 0, doesn't it?
Okay, yes. So.
The question is equal
yes,
0.
Yes,
what?
equal 0. Yeah, so equal 0 is the question. So I think. So in a free field theory, of course, it would be 0 because there would be nothing to create. But in any theory where, there's something can propagate in between, it must be strictly positive. That's obvious. So you're asking, I think, whether I can prove that the only case in which this vanishes is when the theory is free. Yes. Yes.
And but there's the last line of the proof shows that if the vacuum operator acting in the vacuum, 2-point function is positive, the operator acting in the vacuum to any state.
Yes, yes.
0, and you.
Yes, I understand. Yes, yes.
Crossing it really fails.
Yes, yes, yes. So yeah. So basically, you can. Let me just give you one more fact here, which well, it won't answer the question completely. So in 2 dimensions, at this point, I could write a sum rule. I can do the same here, and one finds that there is a sum rule in 4 dimensions, which one can find, and one can check it in many examples. So I'm confident that this is all completely correct. And one finds that it's an integral over some cross-section, which is positive, divided by some kinematical S, ds. So there is some rule like that, where sigma of S is some cross-section as a function of energy for 2 energy momentum tensors to create any state. So in a theory where this is not bigger than 0, but just 0, it would mean that the cross-section. No, the energy here is, of course, time-like. The operators are now. Yes, so what is sigma? Sigma is the cross-section of 2 light-like waves of the energy momentum tensor to create any state with any time-like momentum. So in a theory where, so the argument is this is bigger than 0. In a theory where this is equal to 0, yeah, bigger or equal. In a theory where this is equal, it would mean that the cross-section is 0 at any energy. So basically the 2 light-like waves of the energy momentum tensor do not interpolate to any other state. This cannot be because you can, around the conformal field theory in the ultraviolet, you can do conformal perturbation theory. So you have some control. So I cannot calculate sigma of S in QCD, obviously. I can only prove that it's positive. But you can calculate sigma of S at very large S and at very small s, in the last stages of the flow and in the initial stages of the flow, where the theory is described by conformal perturbation theory still. Okay? And there you can show that sigma is proportional to the beta function squared. So you see that already at very large S, sigma is non-zero. But basically the energy momentum tensor, the trace of the energy momentum tensor is the beta function. So you can show that the sigma of S is the beta function squared times yeah, so you would find that sigma of S is basically the beta function squared of QCD at energy S. And this holds only at very large S when you can use conformal perturbation theory near the UV fixed point. So I know that at very large S and at very small S it's non-zero. So I think I can remove this objection. Okay? Unless it's a free theory where all the beta functions are zero near the conformal fixed points. Is that okay?
Well, that's adding extra dynamic information.
Yes. I need to know that these operators that I'm adding have a non-zero beta function near the UV fixed point. So yeah, so that establishes the A theorem in 4 dimensions. And well, I'll just say a few quick words about the applications. First of all, it applies to QCD, obviously. This kind of things apply to non-perturbative dynamics. You can use the A theorem sometimes to prove that symmetries are broken or symmetries are unbroken. What's the logic? If a symmetry is unbroken, you need to use 't Hooft anomaly matching, and sometimes there are way too many fermions at low energies. And so having this inequality precludes this possibility, because having too many fermions would violate A in the infrared. Then A in the infrared would be way too large, and this inequality would be violated. So you can use this kind of logic to prove that in some models, the symmetry must be broken spontaneously, at least partially. That's very important, of course, with having some particle physics applications in mind. The phases of gauge theories are very important for any kind of applications of strong dynamics at the TeV scale or beyond. You can also do the opposite. Sometimes when a symmetry is broken, you have way too many Goldstone bosons. And then again, you get a violation of A infrared. And again, you can prove that therefore the symmetry must be unbroken. You can also prove that there are no cycles in the renormalization group flows in 4 dimensions, because A always decreases. So if you flow from one conformal field theory to another conformal field theory, there is no way to deform the infrared conformal field theory by some other relevant operator and come back to the UV conformal field theory. So there is a sequence of applications in mathematical physics and also for very pertinent questions about the dynamics of strongly coupled gauge theories that may or may not be relevant for particle physics in the future. And it's definitely true in theories like UCD. The last thing before I close, I'll just tell you what is A in free field theory, so that you have some intuition for how does it measure degrees of freedom. So if you have a 4-dimensional free field theory, so FF is a free field theory, consisting of NB bosons, NF fermions, and NV vectors, then A in some convention is NB plus 11/2 NF plus 62 NV. So this is the formula for how what is this A? How does it count degrees of freedom? It assigns to every scalar weight 1, to every fermion weight 11/2, and every vector weight 62. So you can use this formula in asymptotically free gauge theories to sometimes constrain their dynamics. And there are many, many examples where these constraints are highly non-trivial in supersymmetric and non-supersymmetric theories. So that's a... In QCD, it does not give any interesting constraint on the location of the conformal window. So in QCD, we don't know where is the conformal window. I mean, it's a numerical, of course, a numerical misfortune. But in other theories, which are chiral, you can establish a lot of data about the phases of this theory using the A theorem. In QCD, we don't know where's the conformal window. Otherwise, this would tell us something about the conformal window, which would be fascinating, but it doesn't. Huh? No, nobody knows where is the conformal window. People argue about 9, 10, 11, 12. Yeah, yes. Sort of means plus minus 5. 11 plus minus 5 flavors. So, yes. That's all for this lecture. The next lecture will be about entanglement entropy, which I'll try to explain. It's a concept borrowed from condensed matter physics that turns out to be relevant to A, C, and F, and so on.